All right, in this video, I'll be going through a number of worked example multiple choice questions that are about stationary or standing waves. The first one reads, the diagram shows a long rope fixed at one end. The other end is moved up and down, setting up a stationary wave. What is the phase difference between the oscillations at x and at y? Because x and y are 2 points that are in the same loop of this stationary wave, they must oscillate in phase with each other. Remember that all of the particles that occupy adjacent loops oscillate 180 degrees out of phase. And so all the particles that are sort of occupying the same loop move in phase. All of the particles here on this rope move up together and then move down together. And all the while these particles are moving up above equilibrium, these particles in the adjacent loop are moving down and therefore out of phase. So the phase difference between x and y is 0 because they are in phase. The next question reads, to produce a stationary wave, 2 waves must travel in opposite directions through the same space. Which statement about the properties of the 2 waves must also be true? We know that for waves to interfere, which is what yields a stationary wave, interference between 2 progressive waves traveling in opposite directions, the waves have to be coherent. And coherent means they're going to have the same frequency and a constant frequency. It doesn't change. Well, if they've got the same frequency, they're going to have the same wavelength. And so choice C, the waves must have equal speed, frequency, and wavelength is the correct answer. You couldn't have a wave that has, equal frequency, but a different wavelength if it's going at the same speed. The next question reads, the diagram shows a standing wave on a string. The standing wave has 3 nodes, N1, N2, and N3. Which statement is correct? We can eliminate A because it says all points on the string vibrate in phase. Well, because there's a node here, there's 2 loops, and we know that the particles in these adjacent loops oscillate out of phase, not in phase. The only time that would be true is if we had just a single antinode where all the particles are either above or below equilibrium, then all of the particles would be in phase. But if there's 2 loops, then that can't be true. All points on the string vibrate with the same amplitude. That's not true. We can see that there are points on the string that vibrate a lot, maximum displacement, and there are points that don't oscillate at all. There's no displacement, and there's points in between. So they don't all have the same amplitude. Points that are equidistant from N2 do vibrate with the same frequency because we have sort of the same frequency at all parts of this wave, right? Like everything here is moving at the same frequency, but they're not in phase. The same reason we could eliminate choice A as incorrect, we can eliminate choice C because we don't have points that are equidistant from N2 in phase, but rather out of phase. They will have the same amplitude, though, if they are equidistant from N2. We could go as far over as this point here, and we'd find that an equidistant point here has the same amplitude, right? And so that's that maximum displacement amplitude at the antinode. As far down as this particle of string goes below equilibrium, this particle of string goes above equilibrium. So they do have the same amplitude, which is why choice D is correct. This next question has to do with a dust tube. And it says a horizontal glass tube closed at one end has a layer of dust laid inside it on its lower side. Sound is emitted from a loudspeaker that is placed near the open end of the tube. The frequency of the sound is varied, and at one frequency, a stationary wave is formed inside the tube so that the dust forms small heaps. The distance between 4 heaps of dust is 30 centimeters. The speed of sound in the tube is 330 meters per second. What is the frequency of the sound emitted by the loudspeaker? We have to understand that as the speaker moves air, it's clearing out sort of all of the dust that may be right next to it. And so there's an antinode right here at the speaker. Because this is a closed end, the particles are not free to move left and right at this boundary. There must be a node here, which is why all the dust sort of piles up right here. there must be an antinode here because there's very little dust there. And so as the particles of air move left and right, they sort of clear out all the dust that's sort of around there. And so we see at the low points, antinodes, and there are places in between where there's hardly any movement of air at all. And that means that the dust is going to kind of pile up there. So the dust piles up where there are nodes, and it clears out where there are antinodes. And so I'm just going to label all the antinodes and nodes. And we should be able to identify nodes and antinodes on a standing wave. That's one of the learning objectives. I'm told that between these 4 heaps of dust, there's 30 centimeters of distance. I'm going to draw the waveform with a node going to an antinode, through a node, to an antinode, node, antinode, node, and then reflect back like that. And so here I can see 3 loops of a stationary wave in this 30 centimeters. And how much wave do I have? So here is 1 wave, and I got another half of a wave. So this is 1.5 wavelengths, 1.5 wavelengths, which is 30 centimeters. So that's perfectly solvable. I divide each side by 1.5, and I deduce the wavelength to be 20 centimeters, or 0.2 meters. The velocity is equal to wavelength times frequency. And so frequency is equal to velocity divided by wavelength. The velocity is given, 330 meters per second. The wavelength we just calculated to be 0.2 meters. And so we deduce the frequency to be 1,650 hertz. Choice A. Very similar question, the next one. It says the diagram represents the pattern of stationary waves formed by the superposition of sound waves from a loudspeaker and the reflection from a metal sheet, which is not shown. W, X, Y, and Z are 4 points on the line through the center of these waves. Which statement about these stationary waves is correct? An antinode is formed at the surface of the metal sheet. That's not right, because the metal sheet would prevent any movement. And so it's not shown. I suppose that if students incorrectly think about this as like, well, the metal sheet is right here at the edge of this, then you kind of see that that's an antinode there. But there couldn't be the metal sheet right here if that's an antinode. So it'd have to be like maybe as close as here where there's a node, okay? So a node is formed at the surface of the metal sheet, not an antinode, which is why we can eliminate that answer. A node is a quarter of a wavelength from an adjacent antinode. So if here's a node and I go to the adjacent antinode, that much of a wave is a quarter of a wave. So B is the correct answer, and it's a true statement to have in your notes. For a stationary wave, the distance from a node to an adjacent antinode is a quarter of a wavelength. I would have that in my notes. You know, from a node to an antinode is a quarter of a wavelength. That's helpful to have in mind. The oscillations at X are in phase with those at Y because they occupy adjacent loops. We know that they oscillate out of phase, not in phase, and so that's why we can eliminate choice C. And I spent a moment discussing sort of this one because it looks like the way we've drawn the wave as transverse, that the particles at X here might like oscillate up and down, you know, like from this position to this position. And that's not the case. Sound waves are longitudinal waves. So we really have to hone in on this language here and say any sound wave is a longitudinal wave that moves parallel to the direction of energy transfer. Here the energy is transferred from the speaker this way, so from W over to Z. And even though we draw the wave like this, what's really happening is that at X, the particles are moving the most, okay, left and right. At the node here, the particle just sort of, you know, exists, right? Just, it doesn't have any sort of motion. And if we go a little bit off of that, but not quite at the antinode, we find that the particles are moving left and right, but not as much as like the antinodes. And so it's hard to draw this kind of lateral motion like this, you know, on a 2D sort of sheet of paper. And so we typically represent longitudinal waves like sound waves as a transverse wave, just understanding that it's just a symbolic way to represent the longitudinal motion of the particles. Okay, so D is incorrect because the air particles oscillate parallel to this. You know, X, the particle here, X, is moving back and forth like this. Okay, Now this one is out of phase with it. And so these particles kind of move like this, backwards and forwards like that. If I went over to here and I looked at the particles at the antinodes, they move together. They're both moving like this together, left and right together. These guys move, you know, one's moving to the right while the other one's moving to the left, out of phase, okay? So B is the correct answer on that. Here we can see a musical instrument called a bugle, and it's a long tube with a mouthpiece at one end, and the other end is open and flared, as shown. A musician maintains stationary sound waves with a node at the mouthpiece and an antinode at the other end. The lowest frequency of sound that the bugle can produce is 92 hertz. And so the waveform at that fundamental frequency looks like this. That's 1/4 of a wavelength, right? I have 1/4 of a wave that is 92 hertz. This is the type of wave that is closed at one end, that has an antinode at the other end, open at the other end. And so the next harmonics are going to look like that and that. Okay. So here I've got 3/4 of a wave, and here I've got 5/4 of a wave. Those are the allowable sort of waveforms that permit a node at one end and an antinode at the other end. Note that I can't have a wave like this. That's half a wave because it would have nodes on either end, and I have to have an antinode at the other end. And so if the quarter wavelength is 92 hertz, we can see that that's sort of the first frequency in all of the answers. Well, the next frequency wouldn't be just sort of doubling that because we don't have this waveform. So we don't just double 92 to get 184. Okay, that would be an impossible frequency for this bugle. So it's not 184. We don't just double that. Rather, we have to triple it, right? We have to say each one of these, you know, we're sort of fitting more and more wave in the same length of bugle here. And each quarter wave corresponds to 92 hertz. The higher harmonics are going to be multiples of that fundamental frequency. And so it's going to be the odd multiples, right? So 92 times 3 gives me 276. The next harmonic would be 5 times the fundamental frequency. And so 5 times 92 would be the next harmonic, and that's 460. And so as we mentioned earlier in class, you only need to get to the third harmonic for this question before you realize that the correct answer has to be C. We can eliminate every other answer by that time as being incorrect. The next one reads, the diagram shows a stationary wave on a string at 2 instants of maximum vertical displacement. The frequency of the wave is 12 hertz. What is the speed of the wave? The first thing I want to do is determine the wavelength based on this information. Here I can see that there is 1.5 waves, 1.5 wavelengths equal to 90 centimeters. And so just like I solved for the other one, you know, each one of these is, each loop is 30 centimeters, or I just divide each side by 1.5, and I realize the wavelength here is 60 centimeters or 0.6 meters, right? So it's like 30, 60, 90. So one wave is 60 centimeters or 0.6 meters. If I know that velocity is wavelength times frequency, I can multiply the given 12 hertz of frequency by 0.6 meters of wavelength and get 7.2 meters per second of speed. We also discussed with this question that standing waves don't really have velocity. What we're solving for is the velocity of one of the progressive waves that sort of traveled along the medium and it's reflected, it goes back. So stationary waves don't transfer energy, they don't have velocity, but the progressive waves that make them up do. It's like by the time it's a standing wave, it's done transferring energy. Like we transferred the energy to this point, then it got reflected. Now all the energy is just sort of in the wave, but it's no longer sending any energy anymore. And then another horn question here, musical instrument. It's the exact same type of question with a node at the mouthpiece and an antinode at the bell. They give us the fundamental frequency. And so by now we can just sort of say computationally, I'm going to have harmonics at the odd multiples of the fundamental frequency. And so your first harmonic is that one. The next one would be 75 times 3. And again, it's because we get 3/4 of a wavelength, right? That's 3/4 of a wave where there's a node and an antinode as the next harmonic, right? Remember, the first harmonic looks like that. It's just this piece of it. Okay. And so we would get to the answer D by just multiplying 75 by 3 to get 225 for the first higher note. And then the second higher note would be that next odd integer multiple of the fundamental frequency. This has been some worked example paper 1 questions related to stationary waves. We'll see you next time.